Although the point of that lecture was not Hölder's inequality itself, after I posted that video and it received some good attention, I realized that I personally wasn't too happy still with that proof. It still was too calculational. Something was missing. I personally thought I'm still amazed by validity of this theorem, and somewhere it's still magical. And when you have that feeling, that means you don't really appreciate what's happening. So I gave it a second try, and this time I think I've got it, or at least I have improved upon it. Why exactly is it that Hölder's inequality holds? And here's my new observations. First of all, if you have numbers AI, all of them are approximately 1. Then it's obvious that their average will be close to the average of AI to the p, because in this case AIs are approximately AI to the p with universal constants. And then again, average of numbers all near 1 will also be near 1. And then this number is some number near 1. If you take the pth root, it still remains close to the 1 or to the original values. Therefore, if all numbers are comparable to 1, you get the Hölder's inequality in rather obvious way. Now, why does the Hölder inequality hold for all combinations of AIs, which could have a mixture of really large values, bigger than 1, and really small values, less than 1? The reasoning, I believe, is two things, which are you don't need each individual one of these AIs to be comparable to 1. You only need the average to be comparable to 1. That will be one of the real reasons why Hölder's inequality holds. The next thing, again, another common and very strong tool in analysis, normalization. That by scalar normalization, we can achieve this averaging. And I believe that these two are the true reason behind why Hölder's inequality holds for any collection of positive numbers. To put these observations into a proof, just for completeness, here we go again. You first observe that there are some positive numbers such that this holds for any positive number. And if you want sharp inequalities, you have to show that you can choose a plus p equal to 1. The average. So suppose in the average sense, these are near 1. How does that help? Well, each individual AI satisfies the above inequality. Once you take average of this inequality on both sides, you end up with this. And here is the point of that assumption, because this number is almost 1, so it's comparable to alpha plus beta, which is just a fixed number. But then this number is approximately 1. 1 to the power p is still approximately 1, so everything is comparable up to a constant. Okay, so we proved Hölder's inequality, but under this. Now comes the normalization. So this was the averaging contribution. Now comes the normalization. And here you observe in this is the general Hölder inequality form. You see that if you multiply by lambda AIs and then both sides scale just by lambda. So such an inequality holds for AIs if and only if it holds for any multiples of AIs. And therefore you can choose the multiple to have this approximately 1 or just equal to 1. And therefore case 2 comes in. In some sense, not the main point. So the main point is average. You don't need to assume all numbers are near 1, but you only need to assume in an average sense they are near 1. And of course the normalization. That's it. Sorry, again, I went back to the Hölder inequality, but it had been on my mind for months, and I was trying to wrap my mind around it because it was initially so puzzling and amazing to me. It is still amazing, but in a good sense that I understand at the same time and appreciate why it should hold.